Hello, my name is Xiaoyan, a master student from the University of Ottawa. In this paper, we focus on exploring deep anomaly detection methods based on CapsNet. This presentation will cover these 5 sections: introduction, insight of existing works, the proposed methods, 3 anomaly score functions, experiments and results, and conclusion. First, let's look at the introduction, anomaly detection. Anomaly detection, also known as outlier detection, aims at uncovering abnormal data points, which may stand for novel or alarming events. These are examples of its 4 applications in data centers. It probably indicates an attempt of cyber intrusion. In surveillance system, it could be an illegal traffic flow. And by medical information systems, it means possible onset of certain diseases. In IoT systems, it may represent a hardware failure or alarming event captured by sensors. The contribution of this paper includes CapsNet is explored and tested for deep anomaly detection tasks. Based on unique characteristics of CapsNet, 3 effective anomaly score functions are proposed. The proposed methods are compared with the principal benchmark and 3 advanced deep generative techniques and assessed their capability for deep anomaly detection. Next, let's look at the existing anomaly detection works. In this paper, we summarized the existing deep anomaly detection methods into 2 categories: boundary-based methods and distribution-based methods. In the boundary-based methods, kernel-based support vector domain description (SVDD) and one-class support vector machine (OCSVM) are 2 successful ones for anomaly detection in the pre-deep learning era. However, in the deep learning age, with billions of samples in modern datasets, these traditional methods become less effective. Naturally, they are combined with some deep learning techniques and developed into deep hybrid methods such as VE plus OCSVM and DBN plus OCSVM and one-class deep SVDD. For distribution-based methods, deep generative models such as deep belief net and variational autoencoder can be applied as unsupervised feature learning techniques. Since these deep generative models aim at modeling the joint distribution of visible and latent variables, their likelihood may serve as an anomaly describer. Next, let's look at the CapsNet. This table displays the main difference between capsule and traditional neuron. We can see that in the CapsNet, both input capsule and output capsule are vectors. In the traditional neural nets, both input neuron and output neuron are scalars. In the CapsNet, a capsule is multiplied by transform matrix to produce the transformed capsule, while there is no such an operation for traditional neuron. In the traditional neural nets, there's a W hyperparameter. It is similar to C in the CapsNet. It's a scalar, and W in the traditional neural networks is updated by backpropagation algorithm, while C in the CapsNet is updated by using a new algorithm called dynamic routing. Another difference between them is CapsNet use a new active function, scratch function. while traditional neural networks usually use active functions such as segment tangent rule. Therefore, the CapsNets are able to capture fine transformation such as position, orientation, size, and path-hole relationships, while traditional neural networks are not able to do that. Next, let's look at the proposed methods, three normality score functions. This is the architecture of CapsNet for many studied from the main paper Dynamic Routing Between Capsules. The main structure displayed in Figure A is a classifier, but can also be viewed as an encoder. The reconstruction regularizer can be viewed as a decoder, as displayed in Figure B. In the architecture of the CapsNet, the activation probability of digital capsules at the last layer of CapsNet uses a square function. Unlike softmax probability in convolutional neural network, the activation probabilities of all digital capsules do not necessarily sum to 1. Assuming the network is trained sufficiently well for a normal test image, there should be 1 and only 1 probability being close to 1, representing the possibility of this image belonging to its true class. Based on this property, the prediction probability-based normality score is defined, simply called a PP normality score function. Another normality score function is based on normalized squared reconstruction error, simply called RE normality score function. The reason of using normalized square error instead of mean square error is that since the different objects in the images have different non-zero pixels, for example, digital 8 has much more non-zero pixels than digital 1. Using normalized squared reconstruction error will not weaken the difference between original inputs with small non-zero pixels and its reconstructed version. Preliminary experience shows PP and RE normality score functions can complement each other naturally. These two normality score functions can be combined together. Therefore, the combined normality score function is defined and simply called PP plus RE. Alpha is a combination hyperparameter. Next, let's look at the experiments and results. This figure shows the comparison between two CapsNet-based methods, PP and RE, normally score function, and the 3 baseline models on miniest datasets. From the results, we can clearly see that both CapsNet-based methods outperform 3 baselines at a great degree. Generally, prediction probability based method has a slight higher performance than reconstruction-error-based method. These results show the comparison between two normality score function PP and RE and the 3 baseline models of function miniest and small normal datasets. For function miniest, it seems each method has its own strength, but both CapsNet-based methods are relatively stable and achieved the best results on average. Similar results can be observed from the performance on small knob. We can also see from this result that prediction probability based method and reconstruction error based method can complement each other. By further comparing prediction probability and reconstruction error based methods, one can see that prediction probability based method is more stable and not very much sensitive to the similarity between input images and reconstructed images. When digital 2 is considered as anomalous class, it is reconstructed as different numbers such as 1, 3, 6, 7. It is easily detected by both methods. However, when considered digit 9 as anomalous class, it is in most cases is reconstructed as 4. Such that reconstruction error based normality score of digit 9 is very high. Even so, it is an abnormal class. In these cases, reconstruction error based method doesn't perform as well as a prediction probability based method. Next, let's look at the performance of the combined anomaly score function. This table displays the performance of 3 CapsNet based methods on 4 datasets. As mentioned earlier, since prediction probability and reconstruction error based anomaly score function can complement each other, not surprisingly, the combined methods can take advantages of both methods and perform the best. CapsNet based method PP+RE was also compared with other 4 generative methods. From this table, we can conclude that CapsNet based method achieved the best results among these methods on all datasets except on fashion minutes. Finally, let's look at the conclusion. In this paper, we explored novel solutions of anomaly detection in consideration of CapsNet's distinct characteristics. We devised 3 normality score functions based on CapsNet's activation probability and reconstruction error respectively. Experiments on 4 image datasets show that these CapsNet-based methods outperform existing solutions in many setups. CapsNet-based framework using combined anomaly score function PP+RE can complete quite impressive results on some complicated datasets such as Xiaodan and Smirnov. This paper used vector capsules, matrix capsules using expectation maximization rounding algorithm is essentially an inference technique. It has potential to improve and develop into a fully generative model in the near future. Thank you very much.